Sampling is an integral component of any air pollution control program. Through monitoring, the trends in air quality can be evaluated by comparing the data with the standards. The information so obtained is helpful in implementing control measures for reducing pollutant concentration to acceptable levels and in assessing the effect of air pollution control strategies. While doing this, care must be taken in expressing the average concentrations of air pollutants, since these are different for short and long periods. Sampling procedures are developed on the basis of the pollutant being sampled, the technique of used in the collection, and the device which is being employed, and the sensitivity, specificity, and selectivity of the analytical method being used. Air quality sampling is undertaken usually in two different manners. One of these is the ambient air quality measurement, and the second type of measurement is known as stack sampling. First, we will study the ambient air sampling. The most important objective of any air sampling exercise is to obtain a genuine and representative sample. Now, in order to obtain a good sample, several factors are carefully considered. First of all, the size of the sample required is very important. That is the total volume of air sampled. It decreases with increasing concentration of pollutant and increasing sensitivity of the analytical method. In general, a sample of about 10 cubic meters is required. The sampling rate varies from 0.003 cubic meter per minute to 3 cubic meters per minute, depending on the equipment used. The optimum sampling time for a representative sample is 3 hours. In some cases, the pollutants collected by normal air sampling methods may be reactive, and this results in changes after collection. Therefore, special measures are necessary to minimize such changes. For example, reducing agents such as isopropanol is used as a medium for collecting sulfur dioxide, which inhibits the formation of sulfur trioxide. A typical air sampling system consists of a simple sample collector, a flow meter to measure the airflow through the collector, and a pump to draw the air sample through the system. The flow meter can be positioned either upstream or downstream from the sample collector. The function of the sample collector is to retain the desired pollutant either alone or as a mixture. Sampling of gases and vapors. Several methods are available for the collection of gaseous air pollutants from atmosphere. The most common ones are first sampling, absorption, adsorption, and freeze out sampling. We will study them one by one. First of all, grab sampling. In grab sampling, the sample is collected by filling an evacuated flask. Plastic bags are used for grab sampling. Grab sampling may be taken using rigid wall containers made from glass or steel. These containers are first evacuated and then they are filled by allowing air to enter them. Alternatively, a container may be filled with water and then used as a collector, simply by draining away the water which is replaced by air sampling. Second method is the absorption in liquid. Absorption separates the desired pollutant from air either through direct solubility in absorbing medium or by chemical reactions. The reactive pollutants are absorbed in aqueous solution. For example, sulfur dioxide is absorbed in water or hydrogen peroxide. Ozone is absorbed in a solution of potassium iodide, nitrogen dioxide in sodium hydroxide. Carbon monoxide can be absorbed in the solution of ammoniacal copper chloride. Oxygen is absorbed in the solution of alkaline pyrogalol. Carbon dioxide is absorbed in the alcoholic solution of potassium hydroxide. Oils are used for collecting hydrocarbons. Optimum conditions for efficient sampling are small bubble size and increased residence time of the absorbing device. The ventilation, spraying, and bubbling ensures intimate contact between gas and liquid or solid absorption. Such sampling can also be classified as active and passive absorption sampling. The absorbing devices used include glass scrubbers, packed columns, countercurrent scrubbers. A typical fritted glass scrubber is shown in the figure 1. This shows a schematic diagram of a cascade impactor for the collection of smaller particles. You have the inlet where incoming air contains matter. It moves on to the second chamber, from there to the third chamber. The most widely used collector is the impinger. In the impinger, the gas stream is impinged at high velocity onto a flat surface, thus providing good contact between the gas and the liquid. Common impingers are Greenberg, Smith type, and Midget types. These impingers can handle flow rates of about 30 liters and 3 liters per minute respectively. Scrubbers for sampling gaseous air pollutants is shown in the figure 2. Another method for sampling is the adsorption on solids. Uh, this is shown in the figure 3. In this method, the gas is adsorbed on solid material at reduced temperature and is then evacuated with an inert gas like nitrogen or argon at elevated temperatures. Adsorbents include activated charcoal, activated carbon or alumina, silica gel, Kieselguhr diatomaceous molecular sieves made from sodium or calcium zeolites. The amount of the pollutant adsorbed is proportional to the surface area of the adsorbent, the physico-chemical characteristics of the adsorbent, temperature and pressure maintained in the sampling device. After adsorption, the sample gases are dissolved for analysis. This is accomplished by heating the adsorbent to volatilize the trapped material or by washing it with a liquid solvent. Most organic vapors are analyzed by gas chromatography technique, which directly uses the adsorption principle. But because of many problems associated with desorption of gases, adsorptive sampling is not much used for pollutant measurements. Another technique which is used is known as the cold trapping, condensation, or freeze out sampling. In this, a series of cold traps which are maintained at progressively lower temperatures are used to draw the air sample where pollutants are condensed. Fractionation is achieved by maintaining the first collector in an ice bath at 0 degree centigrade and the last in a liquid nitrogen bath at minus 196 degree centigrade. The samples are then analyzed by means of gas chromatography, infrared or ultraviolet spectrophotometry, mass spectrometry, or by wet chemical means. Coolants used for traps are ice water at 0 degree centigrade, ice salt at minus 21 degree centigrade, dry ice and acetone at minus 79 degree centigrade, liquid air at minus 147 degree centigrade, and liquid oxygen at minus 183 degree centigrade. Although the method is useful for trapping a large number of pollutants for analysis, it is inconvenient to assemble these freeze out traps. Also, there is the problem of accumulation of ice resulting from the condensation of water vapor, which leads to plugging of the system. So, the technique is not generally used for routine sampling purposes. Another method is that of combustion. Pollutants which are oxidizable are exposed to a high temperature of about 650 degrees centigrade. Fertilizers, petrochemical paints, and varnish industries use combustion type of control equipment. But these equipments are very expensive.